All right, everyone, welcome back. We have 5.1 to transform rational functions. And we're going to look at two learning goals: to transform the graph of y is equal to 1 over x, and two, to describe the transformations. All right. Now, something very interesting here is you'll notice the the 1 over x. Okay. This is the first function where we're going to start looking at inputs that are in the denominator's place and the behavior associated with that. Now let's dive into some terminology and our parent function here, okay? Now what is a rational function? A rational function, which is right here, is a function of the form f of x is equal to p of x divided by q of x, where p of x and q of x are polynomials and q of x can't equal 0, okay? And that's very important there. You cannot have 0 at the bottom here. So we have to immediately off the bat say that x cannot equal 0 because you cannot divide by 0. It's undefined behavior. Okay, something very specific to note about rational functions. All right, now that's a real mathematical definition. Okay, so let's break this down. 1 over x is a rational function because it has a polynomial on the top and a polynomial on the bottom. Another example could be this, a much more complicated one: x squared plus x divided by x squared plus x plus 17. Okay, you have a polynomial on the top, you have a polynomial on the bottom. Okay, now you start to think to yourself, well, then anything could be a rational function, and kind of, but generally we're left with kind of that x in the bottom's place. Okay, now a polynomial is a many-term expression, and it has shortcut names of monomial, binomial, and trinomial. So monomial would be x, a single term. A binomial would be x plus 2. A trinomial could be x squared plus x plus 7. These are all polynomials. And you can have more than that. You can have more than 3 terms. You can have 4, 5, 6, 7, 8. It's, really think of a polynomial as just an expression. Okay? Now this one that I put here, we will be solving ones like this in this unit, but we won't be graphing ones like that. That's more of a pre-calculus level rational function. Okay. Now the last thing here is this asymptote, a line that a curve approaches, there should not be a comma there, as it heads towards infinity but never crosses. So there are horizontal, vertical, and oblique asymptotes. And so what this is let's say I had a vertical asymptote, okay, a line, a place on my graph here that my line is going to approach but not cross. And so my function would approach it but never cross it. Okay? And there are a lot of things that kind of get these behaviors in the vertical, horizontal, and oblique asymptotes. But most specifically, it's because of this x cannot be equal to 0. We cannot have a 0 in the denominator's place. Therefore, that has to reflect on the graph. There has to be a place that all of a sudden doesn't exist, but numbers above 0 and below 0 do exist. Okay? So let's break this down a little bit more. Let's actually look at an example. Now, normally in a class setting, I'd be like, we have this function. How could we figure it out? And we would test plugging in a bunch of points and discover what that is. Since I don't have like a live audience for this, I'm going to give you the parent points, okay? But no, if you are ever faced with a function that you don't know what it looks like, that's something you can do. You could start plugging in points and observing behaviors and patterns. Now, the points that we're going to use for x is -2, -1, -0.5, and then +0.5, 1, and 2. This is a very, very important reason why we have these, okay? So when I plug in -2, you get 1 over -2, or just -0.5, okay? And this is your f of x values. Okay, so we have 1 here. -2, -0.5. Then you plug in a -1, you have 1 over -1, which is just -1. Then you plug in -0.5, you get 1 over -0.5. And remember, 1 divided by 0.5. Well, you can ask yourself, how many times does 0.5 go into 1? And that's 2 times. So 0.5 is a negative, so that's -2. Okay. And then we're going to have all the same answers here, except we have positive ones, right? Because if we have 1 over 0.5, whether it's negative or positive, that's going to really be the only difference, is that the answer is a negative or positive, but the number will be the same. So for 0.5, we get positive 2. For 1, we get positive 1. For 2, we get positive 0.5. Okay, and if you're curious as to why this is, think about what happens when x is in the denominator's place. If I had 1 over 10, okay, that's like a dime, that's 10 cents, okay? But if I make that number of x bigger, let's say I make it 100, 1 over 100, well, that's a much smaller number. That's like a penny, right? When you when you increase the value of the denominator, your actual whole number is smaller, okay? So don't get confused by this. The larger numbers we plug in here, generally speaking, for this parent function, the smaller number we're going to get out, okay? Now, this graph on the right here is going to assume just going by increments of 1, okay? So we're going to plot our graph. So we get negative 2 and negative 0.5 here. We get negative 1 here. And we get negative 0.5, negative 2. Okay. Now, that's not a lot of numbers, right? It doesn't seem like it gets to this whole picture here, okay? But remember that we can't get 0, right? We can't get a number of 0. So if I keep adding numbers, if I do negative 3, I start going here, negative 3. Well, I'm going to keep negative 4, negative 5, negative 6. I'm going to start approaching 0, but never cross it, okay? So it's going to be like this, okay? Now you go and probably think to yourself, well, why can't it cross this? Well, we're going to have a horizontal asymptote here at 0. So horizontal asymptote at y is equal to 0, okay? You cannot get an answer of 0 for f of x because you can't plug in a 0 for x. Think about this. With just 1 over x, well, if I plug in any number for x, 1 divided by the number, I get a number, right? So how do we get to 0? Well, you can't. So you can't have a y value of 0, okay? And now let's look at the other one over here. Okay, let's look at the one to the right. You start thinking, well, how can I not approach this y, or this x of equal to 0, and it's the same thing. X cannot be equal to 0 because that's an undefined number. So we get a vertical asymptote of x is equal to 0. Okay, these asymptotes are things that our line is going to approach, but not cross. Okay, now let's finish plotting this. We have 0.5, 2. We have 1, 1. We have 2, 0.5, okay? And so we're not going to cross, and we're not going to cross. And so this is going to be our graph, okay? Now, of course, you always want to do your domain and range, all right? And so, when you really look at this, it's all real numbers, except x cannot be equal to 0, right? And for your range, it's also all real numbers, but y cannot be equal to 0, okay? So, that should make that one pretty easy. Now, of course, we're going to transform these. We're going to move them up, we're going to move them down, we're going to move them side to side, we're going to stretch and compress them and reflect them, and all sorts of things. And so those horizontal asymptotes and those vertical asymptotes will move, okay? All right, now, you really want to make sure you have these points written down. And I would write the x and the y points, simply because these are parent points. We need to start with these every single time, okay? So, okay, this is, now we're really diving into it. So this is the standard form of our rational function. F of x is equal to a divided by x minus h plus k. And we get the same exact behavior that we always get here, okay? So a is going to deal with our stretch. It's going to deal with our compression. And it's going to deal with our reflection, just like normal, okay? H is going to move things to the left and right. So it's going to go left, and it's going to go right. And since it's a minus h, it's always the opposite, okay? So a plus is left, a minus is right. Okay, and now k, it moves us up or down, and a plus is up and a minus is down, just like normal. Okay, with those AHs and Ks. All right. Okay. All right. I think and keep in mind that these H and Ks are going to move your asymptotes also. Okay, because the number that now would get this to 0 is going to change. Okay. All right. So let's look at a little bit of Desmos just so we can see that really quickly. So I got Desmos up now. I have that standard form for a rational function, that f of x is equal to a divided by x minus h plus k. And I just want you to watch how this affects the graph. So this is our parent. I'm going to increase the a value. And you see that stretch, right? It's moving those kind of points out. But if you think about it, if I zoom out, it looks the same, okay? Let me go back to home here. Okay. So let me bring that back to 1. Okay. Now h here, we're going to move. Look at this. I make a positive, it moves it right. And notice how when I make h a positive 5, that my vertical asymptote is where x is 5. Okay. Let me bring that back. Okay. Whoop. And then, whoops, k is at -1. That shouldn't have been there. Okay. And so you can see, oh no, k should have been at 0. H should have been 0. Okay. And now k, same thing. Up moves it up. Down moves it down. And it moves that horizontal asymptote with it. Now watch what happens when I make this negative. Okay, so boom. All of a sudden, it flips it over the, the vertical asymptote. Okay, so watch that again. When a is positive, it's on the right. When a becomes negative, it's reflected like that. Okay, so it's kind of looks a little bit different. Okay, all right. Let's bring this back to our stuff here. Okay. All right, so we're going to do our first actual transformation. That was a lot of building into things. It was the first lesson of rational functions, and we're going to be doing all sorts of stuff with them, multiplying, adding, dividing, some crazy stuff this unit, so I really want us to understand them, okay? Okay, so we're going to need our parent points, all right? So, if you don't have them down yet, you really need to write them down, okay? So x and y. I'm going to write them down here for you again. -2, -1, -0.5. 0.5, 1, and 2, and that should give us out -0.5, -1, -2, 2, 1, and 0.5. So when you're graphing these, those need to be your first points that you plot. Okay, so -2.5, -1, -1, -0.5, -2, okay? And then, what, on the other side? 0.5, 2, 1, 1, 2, 0.5. Okay, now I'm not going to draw the lines yet because we need to transform these. Okay, so just like normal, let's identify our h. So it says a -5, so that means h is 5. We see a k of +2, so it's 2. So we're going right, excuse me, let me just write that in. We're going right 5, and we're going up 2, because it's always the opposite for h. Okay, so I'm going to take all these points. I'm going to do them at the same time. Right 5, so 1, 2, 3, 4, 5. So that first point moves horizontally that way, but it still needs to go up 2 to be right there. Okay, let me just use the pointer for all that, okay? And in fact, actually, after you move this one, so I moved this one 5 spaces over, up 2, you can kind of see that this next one is a half over and down 1. So I'm just going to move that half over, down 1. You see that? And then the next one is 1 over, down a half. I'm just keeping it the same, okay? And then I got to do the same with those bottom 3. So right 5, 1, 2, 3, 4, 5, up 2, 1, 2. So that puts me here. And then I go right 5, 1, 2, 3, 4, 5, up 2. Right 5, 1, 2, 3, 4, 5. Whoops, sorry, up 2, and it puts me there. Okay. All right. Now, our horizontal asymptote also moved. So especially when I do transformations, I like to put these in as dashes so I can see them, because that's at x is equal to 5. And then it moved also up 2 spaces, so I cannot cross these. Now, it's really important to me that you put those in when you do the transformations, because now you can really see where it can't cross, okay? You see that it's gonna approach here and go down, and it's gonna approach here and it's not going to cross. It's gonna be the same thing up here, and boom, okay? And so this is what it finally looks like, but we gotta do domain and range, okay? So all real numbers, except x cannot equal 5, all right? All real numbers, except for y cannot equal 2, okay? All right, so why don't you guys do one now? Give this one a try. Why don't you pause the video, and then I'll go over it. Okay, so hopefully you gave that a try. You should have put your parent points in first, so -2, -0.5, -1, -1, -0.5, -2, like there. And then you have the opposite, 0.52, 1, 1, 2.5, okay? So, we're only really looking at those vertical and horizontal transformations. So we see we have an h of +1, because there's also a -1 here. So we're going right 1. And we have a -3 for k. So we're going down 3, okay? So all I'm going to do is go to these points. I'm going to go right 1, down 3. So right 1, 1, 2, 3, down 3. I started from the top, and I'm just going to go vertically down the points. So right 1, down 3, right 1, down 3, right 1, down 3, right 1, down 3. Am I making mistakes here? Yes, I am. So I think I made a little mistake on that one. So let's try that again. Right 1, down 3 puts me there. Right 1, down 3, right 1, down 3. Okay. And so I'm going to put, before I graph this, I'm going to put in those horizontal and vertical asymptotes. So at h is +1, so we should have our vertical. And then at k is -3, we have our, so I definitely made a mistake there. So that blue point should not have been there. It should have been here, okay? And now I can just graph this. Now, if you didn't find domain and range, you should be doing that on every problem. Your domain is pretty simple, all real numbers, except for x cannot equal 1. And then your range is all real numbers, except for y cannot equal 3, -3, sorry. Okay, now, before we take another step here, okay, if we were in a classroom, I'd probably be sensing some confusion on these horizontal and vertical asymptotes, okay? You have to remember that the denominator's place cannot be 0. So if you think about this vertical asymptote right here, where h is, the x value is 1, look what happens if you plug that in. You get 1 minus a 1, which would be 0, right? And now because we have a missing input, we're also going to be missing an output. And so technically that would have been the number that would have given you a -3. So that's why we're also seeing, whoops, so that was a pointer. So we're also seeing this cancellation out, okay? So hopefully that kind of helps a little bit, all right? Now here's one for me to do, but I want you to notice that there's a 2 in the A place now. And it's a very different problem now, okay? So parent points, we got -2, -0.5, we got -1, -1, -0.5, -2, our standard points. And then we have 0.52, 1, 1, 2.5, okay? And so, I'm not going to touch those yet, but remember the first thing I'm going to do is I'm going to come by and multiply all those points and change them, okay? So I see we have This is 2, 1, and 0.5. Okay, so if I multiply all those by 2, so 2 times 2 is equal to 4. 1 times 2 is equal to 2. 0.5 times 2 is equal to 1. Okay, so these aren't moving anywhere left and right. They're just getting bigger. So 4, 2, and 1. Okay, that's all that they changed there. They're still on the same x, but they have a different y value now. And now we can assume that the other ones are the same, just the negative. So -4, -2, and -1. Okay. Now, that did not take into consideration our horizontal and vertical shifts here. So we have a +3. So that is a left 3. And we have a -3. So that is down 3. So all those blue points need to go left 3, down 3. So I'm going to start at the very top. Okay. So left 3, 1, 2, 3. And then down 3, 1, 2, 3. So I know you can't see me counting, unfortunately, but that top point moved there. Okay. So left 3, 1, where are we at here? Okay. 1, 2, 3, down 3, 1, 2, 3. So I'm unfortunately on top of that other point. And then left 3, 1, 2, 3. Excuse me. Okay. 1, 2, 3, down 3, 1, 2, 3. And I'm on top of that other point again. That's going to make this kind of complicated. So there is still a blue point on these, which I'm going to use arrows. Okay. All right. Now let's do those blue points. Left 3, 1, 2, 3, down 3, puts me here. Left 3, 1, 2, 3, down 3. And then 1, 2, 3, down 3. Okay. Now I'm going to draw my horizontal and vertical asymptotes. So I should have one at -3. And I should have one at the other -3. Okay. Now I can draw my function. And it will look like that. Okay. Now your domain and range, very, very simple again, right? All real numbers, except for x cannot equal -3. Notice how I'm putting that slash through that x, or that equal sign. And then all real numbers, except for y cannot equal -3. Okay? So, now, this one, it gets kind of complicated because it's hard for me to show the counting, right? And it's hard for me, it's hard for you to see how I'm doing that, but just know that I'm shifting exactly how I'm describing it to you. Okay? All right. I think we got one more, and then we got some little bit of math talk, okay? Now, before you start this one, just notice there's a -2 there, okay? So when you multiply, you're going to see a reflection also. So give that a try, and then I'll do it, okay? So pause, try. Okay, so hopefully you gave it a pause. We need to put in our parent points, -2, -0.5, -1, -1, -0.5, -2. Okay, and then the same thing on the top, 0.52, 1, 1, and then 2.5. Okay, now we're going to change the negative, or use the -2 first, right? So we have 2, 1, 0.5. Okay, and I'm going to multiply these by -2. Okay, so we get -4, -2, and then, sorry, that's a point, not a negative. We get -1. Wow, I'm all over the place. Okay. All right, so these green points are now all of a sudden below the x-axis. So this top green point goes to -4. The next green point goes to -2. And then the next green point goes to -1. So it's stretched and it reflected in the same step. Okay. Now, remember, these other ones here on the left, those bottom 3 green points, they would have already been, the -2, -2, -1, and -0.5. So if we multiply with those, we're going to get a positive. So we should have a positive 4, 2, 1. Okay. So this one should jump up to 4. The middle one should jump up to +2. And then that last one should jump up to +1. Okay? Because they should do literally the exact opposite thing. Okay? So those are my red points. Now I got to handle the horizontal vertical shift. So we got +5, which means it is left 5. We have a -4, which means down 4. Okay. So I'm going to all the red points, moving them left 5, down 4. Okay, and I'm going to do that in blue. So let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4 puts me here. So that first point here went like that. Okay, and the next one, 1, 2, 3, 4, 5, then down 4. So we're here. And then 1, 2, 3, 4, 5, down 4. So we're here. So, I mean, you could see that same exact shape. It just kind of moved positions, right? And then the other red points, left 5, 1, 2, 3, 4, 5, down 4. 1, 2, 3, 4, 5, down 4. 1, 2, 3, 4, 5, down 4. Yep, there you go. Okay. Now I'm going to put my horizontal and vertical asymptotes in. So remember, I'm following just off what I see here, right? So this left 5 means it moved 5 spaces to the left. So it's at -5. And then this down 4 means it moved down 4. So now it's at -4. Like that. Okay? And so I draw my graph. Whoa! And I draw my graph. Okay? My domain and my range, all real numbers. All real numbers, except x cannot equal -5 because that would give me a 0 in the denominator's place, and that corresponding output, y cannot equal -4. Okay, now if you're struggling with moving those horizontal and vertical asymptotes, remember they just get moved by the same number, left 5, down 4. Okay, now here's our math talk, all right, and you might be going, man, rational functions, what's the point? I don't really actually need these, right? Well, this is actually a perfect example. Rational functions in anesthesia. So this function right here, c of t, is equal to a times t divided by t squared plus b, where a and t have to do with, you know, a certain chemical drug and its composition, okay? And t is obviously stands for time. And so the outcome is the concentration, the input is time. There's a very specific point here of effectiveness. So if you see these, there's 2 vertical asymptotes here. And that's the reason why these more type are used for pre-calculus instead of algebra 2. You have a duration of effect. So only in between here would the patient be feeling anesthesia, which is very important for surgery. If you've ever had that, you should know. But then there's also a maximum level where that, if you give them too much, they could die. Then it's very dangerous, right? But there's also an effective level. Is the patient actually going to, you know, not feel the surgery and be knocked out for the time that I want? In fact, if memory serves, either this A or B actually has to do with the, you know, the patient. Okay. Now, you know, an anesthesiologist is going to run these calculations with a different type of drug and a different type of patient and make sure that they get those right effective levels so that you don't die in surgery, but also have a safe and effective surgery. Okay. So you're going to see in real life, math does work its way through into lots of different things. Okay. So that's probably an extremely long video, you guys, and I'm just going to wrap it up. So I'll see you guys next time, and yeah, see ya.